And for our last example in section 11.7, we're going to have this series of 2n plus 1 to the nth power over n to the 2n power. So looking at this, we got a lot of n's here, powers of n, bases of n's, and it's like what's going on here. So notice, however, that we have some sort of like function of n raised to another function of n kind of thing going on. And so in that case, usually the root test is really good. So I'm going to go for that. The root test involves taking the limit as n goes to infinity of the nth root of the absolute value of our a sub n, which is 2n plus 1 to the n over n to the 2n. Go. So with the absolute values here, you can do some things for positive n that you can be sloppy with your absolute value algebra because n is positive. So notice I can take out an nth power, which will cancel with my nth root, and that's a pretty critical step in why the root test is a good choice here. So 2n plus 1 over n squared, all that is squared, just getting to the nth power, and then those guys will undo each other. There's the magic. Now all we have left is the absolute value of 2n plus 1 over n squared. So we have the form infinity over infinity. L'Hopital's give L'Hopital some attention here and use that, and I get 2 over 2n, and that goes to 0. So in our root test, we're comparing with 1, so we can come to a conclusion here. When we get a value that's less than 1, we have absolute convergence, which you don't actually have to write that down. If you want to just go to the convergence step, that's fine. But I'm just going to highlight this connection here, that absolute convergence implies regular old convergence. So we can come to that conclusion.